Okay, everyone. Maybe then there were some questions still left. So maybe it's a good idea to very quickly go through the assignment. I'll just skip the introduction because I assume that you all read that. That's not so much point in repeating. These are the important properties for the question. So we have a bilirubin molecule with an absorption of let's say a cross-sectional diameter of approximately 1 nanometer. That's about the size of the molecule. Further in the graph, you can see the absorption spectrum of bilirubin. There's only one catch. It is not the absorption coefficient as we just defined it. So mu a in units of per length, unit of inverse length. It is also per concentration unit. So it is so we now have here the so-called molar absorption coefficient in units of per centimeter per molar. So if you have a certain dilution or of bilirubin, then you need to know the molar concentration as well in order to get to the actual absorption coefficient. For a typical Johannes concentration, we know what that is. We know that the typical concentration is then about 0.2 millimolar, or which you can calculate corresponds to about 10 to the 17 molecules per cubic centimeter. So these are the knowns. Then of course, the question was, iterate for yourself what the absorption efficiency, absorption cross-section, and the absorption coefficient was. What are their units and how are they related? So the absorption efficiency was the ratio of absorbed power and incident power, so that is unitless. Then the absorption cross-section you could find by multiplying the efficiency with the geometrical cross-section. So then this absorption cross-section automatically gets units of area. And then if you have a bunch of molecules and you know the number density, the number of molecules per cubic meter, you can calculate the absorption coefficient by multiplying the absorption cross-section with the number density. So that has units of per length per meter. Okay, so then the second question was to actually calculate that, and then there was an additional bonus question on the last slide. So let's jump straight into the question 2 of calculating the absorption coefficient. So here the first 3 lines on the slide reiterate the numbers that we found on the previous slide. So we know that the molar absorption coefficient at 450 nanometer is given by 50,000 per centimeter per molar. We also know that the typical Johannes concentration is 0.2 millimolar. So we can multiply that out to find the absorption coefficient itself at 450 nanometer, and that evaluates to 10 per centimeter. Steps clear? All right. Then the second question was, what is the absorption cross-section, given that we now know that the absorption coefficient is 10 per centimeter. Well, there again we need to know how many molecules there are per unit volume. In this case, it is easier to use the number density, so that is this 10 to the 17th per cubic centimeter number, and we can then find the absorption cross-section by dividing the absorption coefficient with this number density, this molecular number density. And then the answer I got from that is 10 to the power minus 16 square centimeter for the absorption cross-section. Steps clear? I think this, you can calculate this later on. And then the last question is, what is the absorption efficiency? Well, the relation between absorption cross-section and absorption efficiency was the geometrical cross-section. So there we need to know what the diameter of the molecule is. Well, we had a cross-sectional diameter of approximately 1 nanometer. So that would translate into an absorption efficiency of about 1%. So that means that 1% of the incident power on such a molecule is actually absorbed, and the rest is just passes by. So it is quite a weak absorber, actually. So then our last question was here. So we have this absorption spectrum with a peak at a wavelength of 450 nanometers. So that is where the molecule absorbs strongest, but even there, the efficiency is only about 1%. So if we now look at the competition, that is oxygenated and deoxygenated hemoglobin, which are also present in the blood or around the tissue at least, then we can calculate the absorption efficiency for that as well and put that in a spectrum. And we see that basically, again, for oxygenated in red and deoxygenated in blue, we see that at 450 nanometer, the absorption efficiency of that is much higher than that of bilirubin. So for the hemoglobin forms, it is the efficiency is almost 1. So almost all the power that is incident on such a molecule gets absorbed, whereas for bilirubin it's only about 1%. So the question started actually with the need to have this non-invasive measurement of bilirubin for these neonates, which we don't want to draw blood from that often. But then the question is, how can we now measure such a weak absorber when there is such a very huge background? So of all photons that are incident on blood in that in this case, only 1%, only a tiny fraction is actually absorbed by bilirubin, and the rest is absorbed by blood. So is there a way? Can you think of a way how we can measure this small change over this enormously high background? Any ideas?
Well, we know that bilirubin is derived from hemoglobin, so maybe we can derive this from the other two, from oxygenated and deoxygenated hemoglobin.
Sorry, can you repeat that? Because I missed the first part, I think.
All right, I said that we know that bilirubin is derived from hemoglobin, so maybe yes, maybe we can find some relationship between the two.
Yeah, maybe could be possible, but I was actually looking for a more optical way of.
I couldn't think of one.
Now, so I'll give you a hint. So we have been looking now at 450 nanometer, where the bilirubin absorption was maximum. But of course, you don't have to do the measurement at 450 nanometer. You could also use a second light source, for example, at 700 nanometer, where the absorption of bilirubin is very small, but the absorption of oxygenated hemoglobin is low, but of deoxygenated hemoglobin is pretty high. So if you would do a measurement at about 700 nanometers, then you would know that most of your absorption would have occurred through deoxygenated hemoglobin. The same way, you can pick a third wavelength where the oxygenated hemoglobin has a much higher absorption, for example, and you can do a measurement there, and then you're pretty sure that that all your light is absorbed by that. So if you can cleverly pick a couple of wavelengths and do a couple of measurements there, then you can first from these measurements extract how much oxygenated, how much deoxygenated hemoglobin there is in the sample, and then jump to your measurement at 450 nanometer, where you can now put in the known amounts of hemoglobin, and then you can actually resolve this very small absorption from that. That was the trick I was looking for. Are there any further questions about this assignment? All right, then I'm going to jump back to the other presentation. Okay. Okay, so this is a small recap. This is what we had. We said we put molecules in a cuvette, and we derived the Lambert-Beer law for the intensity E as a function of length through the cuvette L. In that was the absorption coefficient, mu A, units of per meter per unit length, which is the product of the scattering, the product of the absorption cross-section, sigma A, and the molecular number density, rho of n. And of course, that allows you to rewrite Lambert-Beer's law in an even shorter form as exponential minus mu A times L, the absorption coefficient times the length. Okay, so let's assume that these molecules are all homogeneously distributed in the cuvette, and we know basically everything. We know the molecular density, and we know the absorption cross-section of an individual molecule. We also know how thick the cuvette is, and we also know what the area of the laser beam is with which we illuminate. So quick question. Let's say I want to calculate the transmittance, which is given here as I over I0. So that is an intensity at the end of the cuvette divided by the intensity at the beginning of the cuvette. What is that in this experiment? And it is not a trick question. It is mu A, almost. No, not one. I'll give you a quick peek back at the previous slide, the last equation. So I over I0 would then be exponential, exactly. Exponential mu A times L. Yeah, there we go. Which is just basically just Lambert-Beer's law. So this was not so exciting yet. Now let's say we want to do a measurement of the absorption coefficient just using this experiment. So let's say I can measure a transmittance because I can put a detector at the end of the cuvette, so I can measure I, the intensity on the other hand, on the back side. I can make a measurement, a reference measurement of I0 at the front of the cuvette, so I can calculate from my measurement the actual transmittance. So then the question how to retrieve the absorption coefficient from that measurement is basically just one step further from this equation. I have to take the natural logarithm of this transmittance and then divide it by the cuvette length L, which I also knew, and then I have my measurement, and I've made my measurement of the absorption coefficient. Agreed? Okay, now let's make things a little bit more interesting. So we have that same cuvette with the same number of molecules in there, but now by some magic force of nature, we are going to move all the molecules to the front half of the cuvette. So in the front half, I mean that is then perpendicular to the towards the incident laser beam direction. I'm going to move half of them. I'm going to move all the molecules to the front half volume of the cuvette. Question: what is the transmittance in this case? Same I have here. That's probably going to turn out right. Yeah, that answer I really like. You said you write exponential 2 times mu A times half times L, and that is true because what we do now is basically because we move all the molecules to the front of the cuvette, we're actually increasing, doubling the molecular number density in that part. So we get a factor of 2 in front of the molecular number density. But on the other hand, they are all contained in only half the cuvette length. So the length over which the absorption takes place is only in half L. So we get two additional factors, a factor of 2 because we've moved all of them to the front, and a factor half because we now only have absorption over only the half of the cuvette. So then the obvious question is, what would be the absorption coefficient that is measured from this transmittance experiment? Well, the 2 and the half obviously cancel. So in this case, we would get exactly the same value for the absorption coefficient. So, the same answer, yeah. Now, let's move these molecules. Let's move them again. So they were homogeneously distributed at first, but now they were moved to perpendicularly to the beam, also to the side of the cuvette, also to the half of the cuvette. But now not facing the beam, but perpendicular to the beam. So what is the transmittance in this experiment? It's double because I0 is halved. Yes, but I0 is not. I0 stays the same, so there's the same amount of photons that are incident on the cuvette. So what we'll basically see is that that half of the beam does not see any absorbers, so that is just passed through. So on the outside there is a factor half I0 just for the light that has not interacted at all, and then the other half of I0 does interact with the molecules which are now on that side. I can better show the expression now. So we have I over I0 is then factor half. The first half is for the, let's say, for the left-hand part of the beam, which passes without any interaction, and the second term is for the part that interacts. That's also a factor of half, of course. But now we again have that because we moved all the molecules that were originally in the cuvette, we again doubled the molecular number density, so that gives a factor 2 in the exponential. But now the interaction takes place over the whole length of the cuvette, so we have just a factor of L there. So it gets a little bit ugly, a little bit of an ugly expression in this case, because we can now do the same thing. What would be the absorption coefficient retrieved from this transmittance measurement? So again, we would do this measurement. We would normally just take the natural logarithm of t and divide it by L, and that would give us the perceived absorption coefficient. So we can just do that. We can just calculate that. We can take the natural logarithm, divide by L, and then well, the expression that you see here emerges. But the funny thing is, if you plot this, you see that this measured value, this perceived value, will always be smaller than the product of the molecular number density and the cross section. So this measured absorption coefficient is less than the absorption coefficient that we would expect when all the molecules were homogeneously distributed. If they were homogeneously distributed, we would expect mu A equal the number density times the cross section, so the right-hand side of this equation. But now, because of this reorganization, we measure something that is actually less. So not the same answer for mu A. So we have basically the conclusion that we now have, that we can now draw, is that we have the same amount of molecules in this cuvette, but the measured absorption coefficient can still differ. It depends on how I like to call it the organization of the molecules or the organization of the sample. It depends on whether I put whether I homogeneously distribute the molecules, whether I put them to one side or to another side. How I organize the sample, how the molecules are organized, determines this outcome. So now we have to think: does this have any consequences for tissue? Well. If you look at this example, you can at this cartoon again. If we have a hemoglobin molecule, if we would have hemoglobin molecules homogeneously distributed over a volume of blood, then we could just calculate what the absorption coefficient was going to be. But the hemoglobin molecules are not homogeneously distributed. They are inside red blood cells, and typically not outside. So there is already this kind of organization going on for the absorbing molecules. And then you can take it a step further, because also the red blood cells are not homogeneously distributed over a piece of tissue, but they are inside the blood vessels. So there too is a form of organization that makes it a little bit challenging to directly take the absorption properties of a hemoglobin molecule and say something about the absorption of the vasculature that you're actually probing. So in the case of these clinical measurements for the bilirubin meter or for the pulse oximeter, that means that you need to take that into account in the analysis. You cannot just take an absorption spectrum of hemoglobin molecules and then use them. So we need some tool for that, some way of calculating that. And one way of working around that is that until now I've defined the efficiency and the cross section basically for molecules as a property of a molecule. But we can ask the same question: can we also define an efficiency or a cross section on a particle level? So let's say not for a hemoglobin molecule, but for a red blood cell, the absorption efficiency of a red blood cell, and absorption cross section of a red blood cell. So that for the red blood cells is one example. Another example is for melanin molecules. They are also not homogeneously distributed, but located in melanosomes and melanocytes. So for that kind of measurement, you would also want to take this calculation. So let's see if we can. And the first thing, and I have to be very clear on this, is that I have to use two types of densities now. I have to. I'm still sticking with the rho m, the number of absorbing molecules per unit volume in the particles, inside the particles, and I'm going to talk about rho, the number of particles per unit volume in a measurement volume v. So the absorbing molecules are contained in the particles, and the particles are contained in a larger volume, and the density of absorbing molecules in the particle is rho m, molecular as a subscript, and the number of particles in the volume is just plain rho. Okay, one brief sidestep. So if I take this rho, this number of particles per unit volume in the measurement volume, I can rearrange this a little bit to have it equal to the equation there. The ratio of the volume fraction. The volume fraction taken up by the particles in the measurement volume, so that is just a number, a percentage, divided by the particle volume. And you can see that if you bring the volume fraction to the left-hand side and then rewrite a little bit, then it falls out. So you can look at it. You can look at it later. But basically, for convenience, we can define then the number of particles using this density rho or using the volume fraction. In case of blood, this volume fraction has its own name. It's called the hematocrit. You've probably heard from that. Does anybody know what the typical value for hematocrit is? Normal people. I'm not sure if you're looking with half an eye to the Tour de France at this moment, but I do not mean these people. I mean it's 40-45% more or less volume fraction. So that means that let's stick with 45%. That means that 45% of your blood volume is taken up by red blood cells, and the rest is plasma or white blood cells or whatever. But that is what this volume fraction is. So most of it is red blood cells. Okay. So the goal is now to try to define the absorption efficiency and the absorption cross-section, but now not for a molecule, but for a particle. And to keep it simple a little bit, let's assume that the particle is cubic. So it has a volume particle volume Vp equal to r times r, the side of the cube, and it is filled with absorbing molecules. These absorbing molecules have a known absorption cross-section, sigma A, and they also have a known density, rho m. And we're also going to assume that if light is transmitted through this particle, that we can simply apply Lambert-Beer's law to the whole particle. So instead of a cuvette, we're going to apply it to a particle. Okay, so let's say there is an incident intensity I0 on this particle. Then what is the transmittance of one particle? So this is just again, we assume that Lambert-Beer's law holds, so we can just write it down for the single particle. Yeah, so the answer was there. The thing to keep in mind here is that we are applying it to the particle now, which means that the density that goes into this equation is the molecular number density rho of m, and that the length over which the absorption takes place, in this case for this cubic particle, is the side r. So this is then Beer's law applied to the particle. So if we now know this intensities, how can we now calculate the powers that are incident on and that are transmitted through this particle? Remember what the units of intensity were? They were watt per square meter. Yeah, that's correct. So the incident power is simply I0 times G, and G is then the geometrical cross-section of the particle, which in the case of our cubic particle is simply r squared. And we can do the same, actually the same calculation on the other side of the particle, so that will be the transmitted intensity I times r squared. So we can calculate it. Okay, now the bonus question, the final question is, what is the if we now know this, what is then the absorption efficiency of this particle? And then remember what the absorption efficiency was, the definition that we used for absorption efficiency. Yeah, almost there. So I have one that says I over I0. That is not quite the expression I was looking for. And I have PT over P0, which I interpret as transmitted power over incident power. But the definition of the absorption efficiency was the ratio of absorbed power over incident power. So we're almost there. So we can write the absorption efficiency as the ratio of absorbed power over incident power, and the absorbed power equals the difference between what's incident and what is transmitted. So we can write that as the absorbed power. We can write as P0 minus transmitted power PT. Yeah, exactly. Well, and then rework that a little bit. Of course, then going to the right in the equation, the factor 1 is the ratio of the P0s, and we can use the Beer's law now to write the ratio of the transmitted and the incident power, the R squared, again now drop out again. So we have now an expression, and in the most importantly, we again use Lambert-Beer's law, but then applied to the particle. So again, in this exponential, we have the properties of the molecules that are inside this particle. So we've calculated the absorption efficiency of a particle that is filled with molecules that have an absorption cross-section sigma A and that are present in the particle with a molecular number density rho of m. And again, we can combine rho m times the absorption cross-section. We can combine that into the absorption coefficient of the molecules inside the particle. So I have now, I have an expression for the absorption efficiency of one particle as a function of the absorption coefficient of the substance that is inside that particle. Okay. Now, let's continue. If I have an absorption efficiency, I can also calculate an absorption cross-section, right? By the scaling factor was the geometrical cross-section, as we saw just before. So in this case, I need to, I can scale that with the geometrical cross-section of the particle, like this. Okay. Then the almost final question. If I now have these particles, these cubic particles, in a larger volume, taking up a volume fraction f of v, f(v), volume fraction f(v), and I know this expression for the absorption cross-section of the particle. Can I now? What is then an expression for the absorption coefficient of this collection of particles? And then again, you have to look a little bit back to what the definition of the first definition of the absorption coefficient that we gave. So I'm not juggling a little bit with these equations now, so maybe it's a little bit hard to follow, but you can look at it yourself later on. So the basic definition is, so again, I'm talking through the equations from left to right. So mu A equals, in this case of this collection, equals rho, the density of the particles in the volume, times the cross-section of the particle. I was interested in the absorption coefficient of the collection of particles, so that is rho times the cross-section, the absorption cross-section of the particle. We also, in that brief sidestep, said, okay, but we can also write rho, if that is more convenient, we can write rho as the ratio of volume fraction F and the particle volume Vp. So in the second step, I make that substitution. I substitute rho with Fv over V. And then basically all I need to do is combine it with the equation in the first question on this slide. And I get an expression for the absorption coefficient of a collection of these particles, which are present at a certain volume fraction Fv in the measurement volume, and it is expressed as a function of the absorption coefficient of what is inside the particles. Okay. That's that same expression. I'm going to give that a subscript labels sus for suspension because we're dealing with the suspension of these cubic particles. Now, next question. Now let's break all these particles. So we have the same volume, but we break all the particles in such a way that all the absorbing molecules that were inside the particles now get distributed homogeneously throughout the measurement volume. So if you think in terms of red blood cells containing hemoglobin, I could add some chemical which makes the cells burst, and then all the hemoglobin molecules would all of a sudden be homogeneously distributed in the volume. So what is now the absorption coefficient of this new sample, this new solution? What is now the absorption coefficient measured from the solution in terms of the absorption coefficient of what was originally in the particle? So basically what happens is that I had these molecules that were tightly packed in these particles, and now all of a sudden the particles are broken, so all these molecules all of a sudden have much more room for themselves. So basically what happens is that because they are now distributed in more space, they have a fraction equal to the volume fraction, more room. So the absorption coefficient that I would measure in this case is just basically just diluted what was in the particles, will be FV times the absorption coefficient that was in the particles. So if the absorption coefficient of the molecules in the particles was 10 per millimeter, and I had a volume fraction of 10%, let's say, then now because all these molecules have more room for themselves, the measured absorption coefficient of the solution will go down to 1 per millimeter. Is this step clear? Clear enough to continue at least? Because now we're almost there. We now have we are now in the lucky position that we have 3 absorption coefficients. We have one for the stuff that is inside the particles, we have one for the suspension of particles, and we have one for the solution that we would obtain when the particles were broken. So basically this just repeats these equations. The last equation here shows the ratio of the two. So if I divide the absorption coefficient of the suspension by that of the solution, I get this expression which depends on 2 parameters only on the absorption coefficient of the molecules when they were still inside the particles, and the particle size. But all the other factors like volume fraction, they're all gone. So this ratio only depends on these 2 parameters. So now we can so that is for the ratio of these two. If you look at the individual expressions for the mu of the suspension and the absorption coefficient of the solution, then of course volume fraction is still there. So we can write this now to make it a little bit more concrete, specifically for blood, because blood is then basically a suspension of red blood cells. So the denominator on the left-hand side, mu suspension, would be the mu of blood, of a blood volume. In the denominator, we had mu of a solution, which we would get when we would break all the particles, or break all the red blood cells in this case. So that would be the absorption coefficient of an hemoglobin solution, just a solution of hemoglobin molecules. And then on the right-hand side, we have this ratio again, which contains again 2 factors. We have the mu of the hemoglobin solution inside the red blood cells, and we have the size of the red blood cell, the radius. Okay, so is this real? Yes, this is real. If you do measurements on a maybe it's best to look at this slide a little longer. So what people would normally do is to take a measurement on a hemoglobin solution in the lab. So they would make a dilution that would easily fit their cuvettes. They would just simply do a measurement on that solution, and then they would calculate, okay, how many hemoglobin molecules were there in the in tissue, and now I can calculate. Now I can scale to what the absorption coefficient of blood would be. And this equation tells you that actually that is a little bit too simple. If there's you have to take into account that the molecules are packed inside these red blood cells. In the optical literature, this is usually called pigment packaging. This is a paper that from 2004, which and actually it indicates that up until 2004, people knew about this, but nobody really understood it, and nobody really actually implemented it. And then after this paper, people again started realizing, okay, this is actually an issue. We have to take this into account. I will put this paper on Canvas. It's nice. It's nice to read. It's not mandatory, but it's nice to read. Well, then another question is, okay, this was basically relating values for molecules to absorption values for particles. Can we? The question you can ask is, can we scale this even further up? Can we scale it up to the tissue level? And yeah, why not? It basically means just following the same steps. So we start again with defining first the absorption efficiency of tissue simply as the absorbed power divided by the incident power, and then with some choice for the size, for example, the vessel diameter, then we can get to the same kind of expression. So we can get now a second equation that tells us what the ratio is between a piece of tissue where blood is inhomogeneously distributed, which means that it is packed into vessels, divided by the value of the attenuation coefficient that you would get if all the red blood cells were distributed homogeneously, and then you get exactly the same kind of expression, of course, in the same kind of scaling. Okay, I think this has already been pretty harsh on you. So I had an assignment, but I'm going to turn that into a homework assignment. So it is on Canvas already. It basically just is about these factors. What I have provided for you an absorption spectrum of a hemoglobin solution, and what I would like you to do is to convert that using the steps that we just took to an absorption spectrum of blood. So not in vessels, but of blood. I think it's pretty self-explanatory. If it is not, then feel free to contact me at any time, and then we'll start next Friday with discussing that assignment. So this is not, to be clear, this is not one of the graded assignments. This is just for you to get going. Any questions at this moment? All right. Then I wish you a very pleasant afternoon, and I hope to see you all on Friday.